little tricks of the trade and all that good stuff. Just bearing in mind, and I've noticed this throughout the semester, some people are a little bit more proficient when it comes to Desmos than others. And some people are proficient when it comes to Desmos, yet never use it, right? So just understand that Desmos is fair game unless a question tells you specifically that you need to do, show all the work by hand, So we'll just be on the lookout for that. But like, for example, in number 1, it says show that the function satisfies Rolle's theorem on the interval. All right, so you got to do something that justifies Rolle's theorem, but it doesn't necessarily require an algebraic approach. Right, so at least not entirely. So let me show you. So Rolle's theorem requires that you have a function that's continuous and differentiable on the interval. So continuous and differentiable on the interval of -3 to -2. All right, so that's checked out. All right, how do I know it's checked out? It's polynomial functions. Polynomial functions are all continuous and differentiable for all values of x, so we're good to go. All right, but in Rolle's theorem, there's also that extra criteria that f of a has to be equal to f of b. In this case, that means f of -3 has to be equal to f of -2. So to Desmos we go. And what a lot of people have been doing throughout this semester is they make a Desmos, create a link, and then put that in their work and submit that. Question 1, here's my link. Question 2, here's my link. And then some other people have just put like little notes saying, note, here's question 1. And then they just submit the link all in one shot. It really doesn't matter to me. The problem with doing it this way is if you call something f of x for the first question, and then you need to use Desmos again for another f of x, you can get a little conflict with the variables. So that's why people tend to go different Desmoses for different problems, but I leave it up to you to figure that out. So f of x is equal to x cubed plus 2x squared minus 9x minus 18. So we got this good looking function here. I only care about it over the interval of -3 to 2, -3 to -2. So I could truncate this if I want, but I don't really need to get too crazy with this. I just need to know what f of 3 is, f of -3, I keep saying 3. F of -3 is 0. F of -2 also 0. It satisfies both conditions. It's continuous and differentiable on the interval, and it's also the case where f of a and f of b are equal to one another. And then find the corresponding value of c that the theorem guarantees. Right. So for that, I need a derivative. So f prime of x is going to be 3x squared plus 4x minus 9. I evaluate that at some constant c. Right. Rolle's theorem says that if your two y values are the same, there must be some instance where the derivative is equal to 0. Right, and that instance would be the c value. So 3c squared plus 4c minus 9 has to be equal to 0. Not an algebra course. So what I could then do is, I could do this a couple of ways. So a lot I know, but I could plot, 3x squared plus 4x minus 9 as a function. So y equals. And then take note of where they're equal to 0 and only account for the instance in which they're equal to 0 on the given interval, right? So the interval is -3 to -2. So the only value that falls in that interval would be negative 2.523. Right. Alternatively, what I could do is plot f prime of x, right? And I have the derivative. I showed all the work. I plotted my function x cubed plus 2x squared minus 9x minus 18. I would just plot the graph and find the x-intercepts there. You know, the instances where my derivative graph is equal to 0 on the appropriate interval. All right. I only care about -3 to -2. All right. So the question was, how do I add a picture of my work on the questions on the practice test? Oh, you don't need to submit your work on the practice test. It's really all just the last question where you just check the boxes to get the credit. But if you want to send me work so I can look it over, you can do that through email. So then number 2, apply the mean value theorem. All right. And I mentioned this when we were talking about it. The only thing that people, I mean, when people study and they do what they need to do, the only thing they ever mess up is they get the mean value theorem confused for Rolle's theorem and vice versa. Also, the fact that we just learned the average value theorem for antiderivatives. Average value, mean value kind of seems similar, but they have different applications. Right? So you just got to kind of keep that straight. But apply the mean value theorem. It's got to be continuous and differentiable. On the interval of 2 to 4. Right. The mean value theorem says that the slope of the secant line and the slope of the tangent line would be equal at some point along that interval. All right. So as long as it's continuous and differentiable on that closed interval. All right. So what I would do is find f of b minus f of a over b minus a and set that equal. So this is my a, this is my b. And set that equal to f prime of c. Right. So f prime of x is 3x squared plus 1. So f prime of c would be 3c squared plus 1, just evaluating it for some constant c. All right. But then what I would have to do is find the f of b minus f of a over b minus a, which would amount to f of 4 minus f of 2 over 4 minus 2. That I would do in Desmos. All right. So I would type in f of x equal, you know, the given function, f of x equals x cubed plus x minus 8. I'd have my a value, my b value, and all that. But I'm essentially just typing in f of what I have here, f of 4 minus f of 2 over 4 minus 2. So that gives me 29 is equal to 3c squared plus 1. All right. So I have my slope of the secant line based off the given function. I know that that's got to be equal to my derivative somewhere. Now I just got to figure that out. All right. So what I would do here, I turn off my original function, plot my derivative. I mean, unless you want to solve this equation manually, which some people are fine with, some people prefer even, I would want to know where this graph is equal to 29 on the interval. So I would plot y equals 29, find the intersections, but only the relevant intersection would, the only relevant intersection would be the one on the interval. So C would be approximately 3.055. You know, just follow whatever the rounding instructions are on the test, but you know, that's really all I need. I don't need you to show me the algebra, right? The point of the question is, do you know the mean value theorem and how to apply it, right? You've been, I would imagine, assessed enough on how to solve a quadratic. I don't need to see it again, right? And frankly, I don't need to be taken off points for when or if somebody makes a mistake, not on the calculus, but on the part where you solve a simple quadratic. You know, like it's just not worth it, right? For any of us. So that's a nice, concise solution related to mean value. Then number 3, L'Hopital's rule. Right? It doesn't say it, but it is. So if we, because that's, I mean, it's the only limit-based problem in the unit. If we evaluate the function, the first step in any kind of L'Hopital's rule, or really any limit question, is to evaluate the limit first. So 1 minus 2 times the sine of pi over 6 over 1 minus 2 times the cosine of 2 times pi over 6. All right. Sine of pi over 6 is 1/2 times 2 . I'm just looking at the question. Why set it equal to each other? I'm not sure in which step you're referring. Set what equal to each other? These two? If that's the, yeah, I'm getting the set. Yeah, that's the mean value theorem. Yeah. So sine of pi over 6 is equal to 1/2. 1 minus 2 times 1/2, that's going to give you a 0. This here is going to give me pi over 3. Cosine of pi over 3, also 1/2, also going to give me a 0. Right? So we're in a spot here where we have an indeterminate form, so L'Hopital's rule applies. Right? So, and that's because we have 0 over 0. All right. So L'Hopital's rule applies. And L'Hopital's rule tells us to take the derivative of the top separately from the derivative of the bottom and then reapply the limit. Right? Derivative of a constant goes to 0, so I'm not worried about that. Derivative of sine is cosine. So we're looking at the limit. Oops, here. As x approaches pi over 6 of -2 cosine of x. And then again, the 1's going to go to 0. We're not worried about that. Hang on to the -2. Derivative of cosine is -2 sine 2x. So this is going to give me 4 sine 2x. All right, so we just take the derivative of each piece one at a time. All right, again, cosine of 2x has a derivative negative sine 2x times 2. And then since there's already a -2 there, the -2 times another -2 gives you a 4. All right. So then I'm going to reapply my limit, see what happens. -2 cosine pi over 6, 4 sine, really it's 2 pi over 6. All right, so that's -2 times cosine pi over 6 is rad 3 over 2. Two goes into 6 3 times. sine of pi over 3 is also radical 3 over 2, right? So 4 times rad 3 over 2, you get a result of negative 1/2, right? Now, if it's multiple choice question, that would be one thing. You wouldn't really have to show the work, but I wouldn't bet the farm that this one's going to be a multiple choice question, right? Because yeah, it would just be a matter of typing it all in and calling it a day. That wouldn't make it anything more challenging than really a unit 1 question. And what do I mean by typing it all in? I mean, it's still worth it to have an idea of what the answer is supposed to be so that you could check your work. You put the original function in. Right. And then we go and have a look at pi over 6. It's not going to be a point that exists, but what I can do is graph x equals pi over 6 and see what's going on at that location. I can get it in there. It's transcendental, kind of a thing. But at this location here, I don't have a point on this function, right? At pi over 6. I mean, even if it would show up, I could just type it in here. F of pi over 6. Oh, of course, it's something that existed. Wait a minute. That can't be right. I got indeterminate when I plugged it in. I'm just making sure I typed it right. Let me just see something. All right, well, I'll be wondering for the rest of the evening why this played out the way it did, but it is what it is. Well, it doesn't always play out that way, but when it does, it's nice, I guess. Maybe because of it's an irrational number that Desmos just got confused, but it's 0 over 0. It's indeterminate. There should be a hole there, but for whatever reason there isn't. And so we found the flaw in Desmos. Anyway, so yeah, bottom line is you could use the calculator to figure it out. Now later on, I'll probably figure out that I screwed up something, but right now it seems like that's where I'm going. Next up, determine the antiderivative. Every antiderivative question that I would ask you in terms of an indefinite integral is something that could be completed using the rules that we went over, the reverse power rule, those trig rules and all that stuff. Right? So if it's not related to one of those rules, then it has to be some kind of calculator problem. Right? In this case, it looks kind of funky, but I can distribute my x to the negative second and get something that's power rule ready, right? Because remember, this is really the same as saying x to the negative first. So I'm looking at x to the negative second plus x to the negative third dx, anti-differentiate each piece by increasing the exponent by 1, so x to the negative first, and dividing the understood coefficient by that new exponent. So 1 over negative 1, increase the exponent by a 1, divide by that new exponent, add, and throw on a plus c at the end, right? So I'm looking at negative x to the negative first minus 1/2 x to the negative second plus c. And then I look at my choices and I see that there's nothing like those. Well, actually there are, except they're written in a little bit of a different form. Right. So this is the same as saying negative 1 over x. And that's actually enough for me to kind of close in on the correct answer. But just for the sake of it, minus 1 over 2x squared plus c. All right. So that would be choice C in this instance. All right. Number 5. I have not done the second word of the day yet. So number 5, we have a definite integral, but it's a variable bound, but that doesn't impact me. I'll show you. Observe. So 0 to a, I'm going to write this as x to the 1/2 dx. Increase the exponent by 1, x to the 3/2. Divide that understood coefficient by the new exponent. 1 divided by 3/2 is 2/3. Now that's over the interval of 0 to a. You could write x equals 0, x equals a if you want, but like I said, we streamline that. You don't really have to do that. So substitute 2/3 a to the 3/2 minus 2/3 times 0 to the 3/2. Second part cancels away. You're left with just 2/3 a to the 3/2. Looking at our choices, again, similar kind of situation where it's like, all right, we got this answer, doesn't look anything like any of these choices. However, I can eliminate choice A and choice C. It's just a question of whether it's B or D. Now, looking at B, I don't see a radical 3 anywhere in my answer, so I'm suspicious about B. Suspicious being the second word of the day. Suspicious. So I can reorganize this a little bit. Now, when you have a fractional exponent, the numerator is the power, the denominator is the root. All right. If I want to simplify this, I would write it as a times a squared, so that I would have an even power under the radical. So radical a times radical a squared with the two, well, I don't know why that happens. With the 2/3 out in front. The square root of a squared is a. We have the radical a and we have the 2/3 all multiplied. And looking at the choices now, you see that that's, it doesn't take much doing to make that equivalent in appearance anyway to choice D. So yeah, a little bit of a fundamental theorem, but nothing too crazy. Just you're substituting a variable in. But this is the kind of question I like to throw on there, because I don't want every single definite integral problem, the ones with the bounds, to be ones that you could just chuck in a calculator and call it a day. I want to demonstrate some skill. So then number 6, those are the properties of integration that we were working on just a little while ago. Which of the following is a correct statement if, it's kind of hard, it got cut off a little bit, but that's supposed to be a 9. I'm sure you can make it out. Look carefully enough. Looks like a G actually, the way I just wrote it. If the integral over the interval of 0 to 5 is equal to 9, and the integral over the interval of 2 to 5 is equal to -1. All right. So it's asking us to figure out, well, which one of these would be true. I mean, we could always start off with which one of them would not be true, but let's just go with true first, right? Or at least whatever we can figure out based off the information that they've given us. So I know that I'm starting off with a low bound of 0. So if I'm just looking at it as a simple number line, I got a 0 and I got a 5. All right, both of the upper bounds are 5. The lowest bound that I see here is a 0. I got a 2 along the way. All right. Now, I don't know what this graph looks like, but over the interval of 2 to 5, I know that that's got to give me part of that graph below the x-axis. Or I mean, that entire part of the graph has to be below the x-axis because I have a negative area. The other part has to be above the x-axis because I have some sort of positive net area. And in order for that to have been offset to end up with a positive result, whatever came after 0 to 2 must have been something sufficiently large to offset the -1. So it couldn't have been more negative. It had to be positive, right? It may not have been very, very positive, but it had to be somewhat positive, all right? So if I take the integral over the interval of 0 to 2 of f of x dx, add that to the integral over the interval of 2 to 5 of f of x dx. Oh, sorry, I got that. I apologize. I got that backwards. I'll fix it in a second. I'll get 0 to 5 f of x dx. Yeah, no matter how many times I looked at it, I kept seeing, when I saw it, it said 2 to 5 here, but I kept seeing 0 to 2. I don't know why. So let me just fix this graph. Oh, it looks like a closed eye. All right, so this part has to be positive. And this part has to be some substantial negative value in order to end up with a positive result after this interval. All right, but we don't know what it is. We're going to solve for that. All right, so there's no scale to my graph. I mean, this actually could be, very tall. Like I just don't know. All right, but we know we're going to have some positive, some negative, and then the result itself is going to be positive. All right, so we know that this is going to be a -1. The whole thing is 9. This piece is -1. So this is the unknown. But really, it's just a matter of adding a 1 to both sides to figure out what that other integral would be. All right. So that's got to be equal to 10. All right. So again, not drawn to scale. It's probably going to look something more like this. So we'd have 10 here, then the -1 there, but that's a hindsight. I suppose I could have just looked at the choices and figured that out, but I didn't. So right. So something like that. Right. But now looking at the choices, I see I have on the interval of 2 to 0, a +10. 0 to 2, I have a -10. 0 to 2, I have a +10. That's the one I want. But I got to be careful because sometimes they can mess with you a little bit. And, maybe choice C isn't there, but what they'll say is over the interval of 2 to 0, we have a -10, right? One of those properties that we talked about, this is the same as from 2 to 0 of f of x dx would be equal to -10. Right. So if we had gone the other way, it would be a negative value, and that would have been correct. That would have also been correct. So you got to be careful about things like that. And that's because of the rule from a to b of f of x dx is equal to negative b to a of f of x dx. All right. So these kind of problems could be a little bit on the mind-bending side, but for me, it helps to have a visual. Not everybody agrees, but that's kind of my thought process. All right, so this is more for learning, but whatever. All right, number 7, antiderivative. Well, if you know your rules, d dx of tangent of x is equal to secant squared. So we have a negative coefficient here. I can factor that out, constant multiple rule. Now I have a 2x here. I got to decide how that's going to play into this. But I got to figure it's going to be a tangent in some capacity. I'll say negative tangent. The argument is 2x. It's just a question of, is that going to be my antiderivative or is there more to it? Well, if I had the derivative, or if I had the need to take the derivative of negative tangent of 2x, I'd have the negative, tangent would become secant squared of 2x, but then by chain rule, I'd have to multiply by the derivative on the inside. So I'd actually get double what I would really want. And so to correct for that, I would do the exact opposite. Instead of multiply by 2, I would divide by 2. So multiply by 1/2 or just divide the whole thing by 2. And so that would be my antiderivative. You could write it in a different way, or negative 1/2 tangent 2x plus c. But the idea is to kind of have a suspicion of what you think the antiderivative is, test it out by finding the derivative and see if it works. Another way to handle that would be on Desmos. You know, like if you suspect that the derivative, the antiderivative of negative secant squared 2x is just negative tangent 2x, what you can do is you can put that in. F of x is equal to negative tangent 2x. Plot its derivative. Right? Do some zoom in until you get where you need to go. You see that this is the derivative function of negative tangent 2x. Right? Now, if that's equivalent to negative secant squared 2x, then you're good. If it's not, then you're not, but it's not all over at this point. You can salvage it. Right? So I could look at this and say, all right, well, let me put in my secant, square it, pop in my 2x. You see it's got the same structure and shape, but it's a little off, right? What is it off by? Some constant multiple. So what I would do is multiply this by some value a, create a slider for it, and just start sliding around. Oh, sorry, not the function, the derivative. So multiply what I think the derivative is by some constant value a, and slide it around until I get a match. The match happens when the x value is equal to 2. So that tells me that I needed to actually have a 2 in my integral in order for this, my suspected antiderivative to be correct, right? So that means that, you know, that multiplier here had to be a 2, so you would correct for that by dividing by a 2. Could also have done it with the way I started doing it, but either way. All right. Number 8, this is the average value theorem, and on the test I'll put the hint there too, because when they ask you for the mean, it's not always clear, especially since the framework of the problem is pretty much the same. But this is the average value over the interval. So 1 over b minus a over the interval of a to b of f of x dx. So 1 over 5 minus negative 5 over the interval of negative 5 to 5 of the function 25 minus x squared dx. Now this is it's all straight calculator, right? This is the point of this question is for you to demonstrate that you know what the average value theorem is, not that you could show me really Calc 2 level integration techniques. But yeah, I mean, this part you could do by hand. That's a 1/10. But then everything else just chuck right into the calculator and just let it spit out the answer. Right? And then, sometimes, just read the questions on the test, because sometimes I don't even ask you to give the answer. Sometimes I say, write an expression that could be used to find the average value over the interval. So in that case, I'm not even looking for the function, or the answer, I'm just looking for the function. So pop it in, slap a dx on it, and call it a day. And so approximately, and I'll give you rounding instructions on the test, but this is about 3.927. In most cases, it's going to be the nearest 3 decimal places, but there are some exceptions to that. All right, so that was 8. Number 9 is actually designed to be a gift. All right. It just doesn't seem like it would be. I just want to make sure that I've given you all the present that I intended to give you. Yes. All right. So if you go into the Unit 3 folder under calculators, so the Unit 3 calculators folder on Blackboard, you'll see the gift that makes this problem less complicated than it would be. Because you might remember, we spent a while doing this stuff by hand, and it wasn't pretty. All right. But I created a calculator that will do all this stuff for you. All right. So which of the following is the right rectangular approximation of the area bounded by the curve? As long as you know that the bounded region spans from A to B, and the number of subintervals is the value n, then you'll be able to use this calculator. Because all you have to do is put your unique function in there, whatever it is for the problem at hand. Let me just get rid of that. I put a placeholder function in there. Everything prior to the squiggly brackets. All right, leave the squiggly brackets alone. Definitely easier on a keyboard, but all right, so x root 9 minus 5x squared. That's a nice representation of the function. The a value is 0. Come on. I said, come on, I'm not listening. Okay, I got to type it in. That static cling. All right. The b value is 1. Always try. I don't know why I even bother. Okay, no, because it works like the one time. The n value should be 4 for this problem. So you see that there are 4 rectangles there, each of which are connected to the curve in their upper right-hand corner. All right, so your a value, your b value, and your n value. Then you'll see MRAM, LRAM, or you see trapezoidal approximation too, and RRAM, and then some side computations. But I'm only going to ask you about the 2 things that we covered in this class: LRAM, left rectangular approximation method, and RRAM, a right rectangular approximation method. So there's 2 folders here. This is the right rectangular. This is left rectangular. And this is what middle would look like if you were interested. But you tap on the folder that says RRAM. So this is RRAM. Hit the little drop down, and right at the bottom, it'll say right endpoint approximation. 1 point, it would round to 1.499. This, like I said, it's supposed to be a gift. All right. So you just go to the appropriate folder, pull the answer, and call it a day. There will be a problem just like this on the test. I think, I honestly, I can't remember. It's either RRAM or LRAM. So just pay attention. If it says right rectangular approximation, it's RRAM. If it says left rectangular approximation, it's LRAM. All right. Super easy, barely an inconvenience. And then the pièce de resistance. Find the limit, or using the limit definition of integration, find the definite integral of this, right? Oh, no problem. So this one is a compensation for the previous one. So f of x is equal to negative 2x squared plus x. So that's my function, but I only really care about it over the interval of 0 to 2. All right, so that's this interval here. All right, so that's a crazy looking interval, but it's still an interval and it's still fine. We'll get an area over that interval. Now, we already know other methods for finding the definite integral. I mean, it would just be a matter of saying the antiderivative over the interval of 0 to 2. We should expect some negative value here. So negative, I mean, if you want to have as a fraction, negative 10/3, because we have a lot more area below the axis than we do have above the axis, right? So it's going to be interesting, but like you have the answer going into the problem. It's the process that I care about here. Right? Now, just in terms of what we're actually looking for, we would have 0 less than or equal to y less than or equal to f of x. So we would need that area, but then we would also need the area between the function on the low side. So these two areas put together, that's what's going to give us the negative 10/3. Now, that's all well and good, but when we're using the limit definition, it's a particular approach. First, we identify the delta x. Delta x is b minus a over n. All right, so this is my a, this is my b. So 2 minus 0 over n. So 2 over n. Then we figure out a plus I delta x. So the a value is 0. I times delta x, which is 2 over n. So 2i over n. So then we compute f of a plus I delta x, which is going to replace the x's in the original function with this expression. So we're looking at negative 2 times 2i over n squared plus 2i over n. So we'd simplify that. Yeah, I knew. Simplifying that, negative 2 times 4i squared over n squared plus 2i over n. Get a little common denominator action if you want, or you could just kind of leave it apart for the time being. So this at least would be negative 8i squared over n squared plus 2i over n. Right? There's pros and cons either way of either putting it together or keeping it apart. What I tend to do is wait to see how things are developing before I make that decision. And the next step is really where things start kind of falling into place or not. So f of a plus I delta x gets multiplied by delta x. So this expression is going to get multiplied by 2 over n. Right? So that's going to give us negative 16i squared over n cubed plus 4i over n squared. So then things get uglier before they get cleaner, but they will get cleaner, but we do have to apply the summation. So the sum from I equals 1 to n of this. But we can split this up by the plus sign. So that would be the sum. And you can write it without all the trimmings if you want. You don't have to put the I equals 1 to n. You do it the first time and you do it the last time, but every step of the way along the middle, you don't really have to write it. I'm going to write it, but I just like to let people know that. This would be negative 16i squared over n cubed plus the sum from I equals 1 to n of 4i over n squared. Now, if it doesn't have an I in it, if it's a factor that doesn't have an I in it, it doesn't need to be part of the summation. So I can pull out the negative 16 and the n cubed and just leave the sum of I squared. I could pull out the 4 over n squared and leave the sum of just I. All right. Now, these are two rules that you need to access, be mindful of, I guess. Not the easiest things in the world to remember, so definitely keep that page handy. But you got n times n plus 1 times 2n plus 1 over 6. And then n times n plus 1 over 2. All right. So if you need to refer to, I'll come back to this in a sec, but if you need to refer to them, they're in your packet under integration stat page 63. Right. So the ones I'm using are these two, but it's page 63. That's where you want to get this information. All right. So then the summations are gone, which is great news, finally. We can simplify as much as possible and then find the limit. Ultimately, we're going to find the limit as n approaches infinity of all of this stuff here. It's just a question of, like when you're ready to do that. Right? So it usually requires a little bit of distributing to get that accomplished, but it's easier to simplify down before expanding out because n goes into n cubed n squared times, n goes into n squared n times, 2 goes into 4 twice. These two divide. You could divide both of these by 2, so negative 8 and 3. So you'd have the limit as n approaches infinity of negative 8 times n plus 1 times 2n plus 1 over 3n squared plus 2n plus 1. So really, I could just distribute it 2n plus 2 over n. I'd have to distribute these two pieces here. So that's 2n squared plus 3n plus 1 multiplied by the negative 8 all over 3n squared. Everything else comes along for the ride. So negative 16n squared plus or minus negative 24n minus 8 over 3n squared plus 2n plus 2 over n, and you have your limit as n approaches infinity. So using whatever rules you like, whether it's L'Hopital's rule or just basic limit rules, you can find the limit of each part of this. Right, so this would be, by the end behavior model, negative 16/3. This would be just a 2. Right. So as a result, you would finally at long last get negative 10/3. All right, but that's the big one, obviously. All right. I won't ask you anything that complicated, but you will have to do that process.